Okay, so I want you to try example 3. Okay, so I want to remember what we talked about last time, which was whatever I do to that, I'm going to also do to that. So whatever I do to my equation, I'm going to do the same thing to my delta H. So try to figure this out, pause the video, and then we'll start back up again. Okay, so you took some time, you dove in, and let's see what we were looking for. So they said calculate the delta H for this reaction, right? So we're looking at delta H, and what did they do? So that's what we have to figure out. What did they do? All right, so see if you could figure this out. So the first thing is look at this. The reactants were the products. So what did they do? Well, they took the equation and they flipped it over. So if you flip an equation over or you reverse it, you also are going to flip the delta H. So they reversed the equation. It's backwards. So they reversed the equation. So we're going to do the same thing to our delta H, which means that we're just going to switch the sign. So that's what you would do there. We're going to switch the sign. Okay. So first thing we do is our delta H now equals negative 595.5. Okay. Now, let's go ahead and take a look at what they did to these values. So like this used to be a 4. It's now a 1. This used to be a 2. It's now a 1/2. So this is a 1. It's now a 1/4. So what did they do? They divided everything by 4. So they divided everything by 4, or what we're looking at is 1/4 of the original value. Okay, so we're gonna also divide by 4. So let's go ahead and write it out. This is what we would have. We'd have Ag as a solid, and then we got this H2S as a gas, and my 1/4 oxygen. So it looks kind of weird, but really this is pretty straightforward on how you solve it. And so I'm going to take the 595. So my delta H, and I'm kind of running out of space here, is going to equal negative 595. Oops. 9. There we go. And I'm going to divide that by 4. Okay. So key thing is we've got to remember that this negative sign right there, that's like really important. A lot of times what students get wrong on these is the sign. Like the sign is very, very, very important. So, and so we're going to end up with negative 148.9 kilojoules. All right. So there it is. There's the answer right there. And hopefully you spotted that. Now, maybe you didn't. I mean, there were some tricks there, right? Like there were some things we hadn't talked about. But now that you see it, should be able to figure it out. So, all right. Now let's slide down here. Let's take a look at stoichiometry. So there's our favorite. Spend a lot of time with stoichiometry, always talking about stoichiometry. So remember that when we say something like a stoichiometric calculation, we're just going from chemical A to chemical B and using delta H as a conversion factor. So let's think about what delta H is. Delta H is a fantastic conversion factor because it's per mole. So what delta H equals is it equals some amount of kilojoules for every mole. Now, this is kind of weird because it depends on your chemical. So if I go back up here and we just grab something randomly here. So like right here, 1/4 oxygen. So what does negative 148.9 mean? It means you get a negative 148.9 kilojoules for 1/4 of a mole of oxygen. That doesn't mean you get negative 148.9 for one, it's for a quarter. You get negative 148.9 for 1 mole of silver, for half a mole of H2S. And so it's kind of different, but you have to just consider what goes here. Oops. What goes here is the coefficient. So it would actually be like for the oxygen, it would actually be negative 148.9 kilojoules for every 1/4 of a mole. All right, that's not a super clean one, but that's what it would be. So you could take negative 148.9 divided by 0.25, and that's how many kilojoules you get for a single mole. So it is a good conversion factor. So let's take a look at the next example here. And the next example is going to dive into using this as a conversion factor. So the first thing we got to look at is we've got a formula and it is balanced. And we got a delta H. So let's do what we've always kind of done, is put our pieces where we want them. So we got calculate delta H when you have 2.50 grams of hydrochloric acid formed by the following reaction. So we know how many grams of hydrochloric acid we have, but that's not moles. So what you have to remember is that 250 grams is not moles. So we have to convert that over. Once we convert that over, we can use this conversion, which this is going to say for hydrochloric acid, delta H is going to equal negative 185 kilojoules for every 2 moles of hydrochloric acid. Not a very good looking C. And so because there's a 2 here, there's not a 1 on the bottom. Okay, so just be aware of that. So let's set this up. Same kind of as any problem you've ever done. So write down the number they give you. Write down your chemical. Convert it into moles. So this is just adding up hydrochloric acid, right? Like we've done this a billion times. So 36.46 is what you're going to get from the periodic table. So I'm not making this number up, right? Just looked it up on the periodic table. And then that's where the new piece comes in. So right here, we're going to use our conversion factors. Look how well it works. Negative 185 kilojoules for every 2 moles of hydrochloric acid. We don't know how many moles we have. We've got grams, so we go to moles, and then that's the ratio. So we run this through a calculator, and I got my calculator here. So let's see what we get. So we get a 2.5 divided by 36.46. Hit enter. Multiply by negative 185, hit enter, and then divide by 2. And that's how many kilojoules you would get if you had 2.5 grams. If you had 5 grams, you get more. If you had 75 grams, you get more. But we have the 2.5 grams, and so that should give us negative 6.34 kilojoules. Okay, so this is in the lab. You could actually go and figure that out, and you could say, okay, I can measure mass in the lab. So I can measure something like 2.5 grams of hydrochloric acid. I could do this particular reaction here, and then I should expect that if this reaction happened, if I did get 2.5 grams of hydrochloric acid, I should be getting negative 6.34 kilojoules of heat. That it should be exothermic, that it should warm up. So good example. And we use this idea of delta H as a conversion factor. We use that as we keep moving forward and practicing. So great example. Okay, so now let's kind of do a little bit of an overview here, and then I'm going to probably stop this one. And what are we going to dive into now is calorimetry, and that's just a fancy word for measuring heat in a calorimeter, which a calorimeter is just going to be something pretty simple like a couple of coffee cups. So not a ton of time here, so I'm going to pause this, and we'll pick it up on the next one.